So in this segment we're going to look at the case of a mass falling while being attached to a rope that is wrapped around a pulley. So here's our pulley. It's a massive wheel, mass M and radius R, and a line is wrapped around it, and the line hangs down and is attached to another mass which we'll call little m. So as the mass is dropped, it pulls, exerts a force on the pulley, that force exerts a torque, and that causes the pulley to rotate, and the mass will fall all the way down. So the first part of this problem, we're going to use the conservation of energy to predict what will be the velocity of the mass falling as a function of the height that it has travelled. So let's imagine that we've fallen a distance h. We can say that the change in gravitational potential energy associated with moving this distance h will be equal to the gain in kinetic energy of the mass which will be moving and of the pulley which will be rotating. So delta GPE equal delta kinetic energy, so m, which is the mass of the small hanging mass, times g, the gravitational acceleration, times h, the distance that it happens to have fallen, will now be equal to 1/2 mv squared plus 1/2 I omega squared, where I is the rotational inertia or moment of inertia of the pulley. So if the pulley is a flat, thick, heavy disc, then I for a disc or a cylinder is equal to 1/2 m r squared. Omega, you remember, is the angular velocity. And the angular velocity and the linear velocity will not be constant in this problem. In fact, the mass will be speeding up as it falls down under most conditions. So our calculation, of course, is for what is the speed of the object after it has fallen a distance h. So that is what omega and v represent. They represent the speed of the system at some specific instant in time and space. So because we're using the conservation of energy method, we don't actually have to worry about their time dependence. It's built in. This is one of the beauties of using the conservation of energy method. So if you remember, omega is equal to v over r. So if I make all those substitutions, I now have 1/2 mv squared plus 1/2 times I, which is 1/2 mr squared, and now I now have times v squared over r squared, because we have omega squared. So we see that the radius of the pulley miraculously cancels out. So we now have 1/2 mv squared plus 1/4 mv squared equals mgh. So we can now rearrange these terms to get v as the subject of the formula. It will probably be sensible to divide through by the small m so that we end up getting the answer in terms of the ratio of the masses of the two components in the system. So let's do that now. So we've got gh equals 1/2 v squared plus 1/4 m over m, the ratio of the masses, v squared, and of course we can take 1/2 v squared out as a common factor. So now we have 1 plus m over m over 2m equals gh. And now all that remains to be done is to rearrange this formula to give v or v squared. So let's see, v squared now is going to be equal to 2gh over 1 plus m over 2m. That's a big M. And there we are done.